Good morning, everyone, and a warm welcome on behalf of the Wilhelm Heraeus Foundation to this Breakthrough Symposium this morning. It's a pleasure to be here and say a few words about the foundation. For those of you who joined us for dinner yesterday, they already learned quite a bit about the foundation, but I hope that I'm able to add some further information. So first of all, who were Wilhelm and Else Heraeus? Wilhelm Heinrich Heraeus was born 1900. He studied physics, mathematics in Bonn, Göttingen, and Munich, and then he moved to the University of Frankfurt, where he completed his PhD in physics in 1923. So at the age of 23, which was not uncommon at that time. In his CV, he writes that his advisors were Herr Geheimrat Wachsmuth and Herr Professor Gerlach. So this is, of course, Walter Gerlach, who today is best known for the famous Stern-Gerlach experiment, the first experimental demonstration of quantization of angular momentum. So these were the exciting years where quantum mechanics was developed. And you know, we are this year in the International Year of Quantum Physics. But Wilhelm Heinrich decided to leave academia, and he entered the company his grandfather has founded in 1851 in Hanau, a small town some 30 kilometers east of Frankfurt. And he spent his whole professional career as entrepreneur and manager in this company. As he and his wife Else had no kids, and they decided in the 1960s to found this foundation. After they passed away in the 1980s, all their company shares were transferred into the property of the foundation. And today it's the dividend of these shares which constitutes our regular income. So if the company makes money, they pay us a dividend. It's good for us and it's good for you because we can support and fund activities like this symposium and many others. So as the money comes from the company, let me just say a few words about it. It's a globally active company, one of the top 10 family-owned companies in Germany, which includes business in different sectors. And just to give you two examples which are very strongly related to physics, Heraeus delivered several tons of ultra-pure niobium for the superconducting accelerating cavities, both of the Large Hadron Collider at CERN and the European X-ray free electron laser in Hamburg. And another example, the right picture shows two of the mirrors of gravitational wave detector LIGO, and the blanks of these mirrors were also manufactured by Heraeus. So now coming to our activities, we do support research and education in science with an emphasis on physics by, for example, funding school activities like school labs. We fund teacher training courses. We support early career researchers with a whole bunch of different activities. We organize and fund scientific events. We cooperate very strongly with the German Physical Society, DVG, and there are many other activities I'm not going to mention in detail. Just to give you a glimpse about some activities related to education, so we do fund school labs. For example, there's a picture here showing a school lab dedicated to environmental physics and spectroscopy. Many activities are also related to astronomy. We do fund different prizes and competitions like Jugend forscht in Germany. And we fund and support teacher training courses in order to bring more modern physics to schools. Then another big group of activities is related to scientific events like the Heraeus seminars, which are often compared to Gordon conferences. So there are 60 to 80 people, workshops with seniors and early career researchers on all topics of physics and interdisciplinary areas. And more recent activity are the binational seminars. Here the idea is to initiate new or foster existing collaborations between working groups in Germany and the partner country. We started this activity with European partner countries, but meanwhile extended it to other countries, especially from the Global South. We had several seminars meanwhile with Brazil, on Argentina. We'll have one with South Africa and others. Many of these activities take place at the Physikzentrum in Bad Honnef. It's a wonderful conference center, and I'm sure many of you have been there before. But we also support many activities at other European conference centers like the École de Physique in Les Houches or the Ettore Majorana Foundation in Erici. And recently we also started a cooperation with the International Center for Theoretical Physics, the ICTP in Trieste. Finally, I just want to mention a few activities related to early career researchers. Almost 10 years ago, we started an activity called Leading for Tomorrow. So it's a leadership program for early career researchers. This is run by the German Physical Society, financed by us. And next year there will be the 10th year of this activity, and I know that several alumni of this program are here as well today. Welcome. We also started 2 years ago a program, an internship program, where PhD physicists with a PhD can spend 3 months in the German Parliament. It's also a very interesting program, and I know that there are also some of these here, so welcome again. And finally, 2 days ago, we had our annual meeting, the so-called Heraeus Forum, and for the first time, we awarded 5 young researchers with the Heraeus Research Fellowships. The idea is something similar to the Alfred P. Sloan Research Fellowships in the US, and here we want to support young researchers who are not yet tenured, but already have a very promising career, and this is one of our latest activities. So my time is almost over. I hope you enjoy as much as possible this symposium here, and before I end, I want to say thank you on behalf of the foundation to you both here, Thomas Elsässer and Jigdem Esivir, for organizing and chairing this session this morning. Thank you very much.
Good morning, everybody. So I welcome you to this symposium on this early morning on Saturday. I'm Jigdem Esivir. I'm a particle physicist, experimentalist. I'm working at the Atlas with the Atlas experiment at the Large Hadron Collider since many years. And I'm with the Humboldt University of Berlin and DAISY, which is a Helmholtz Institute just right outside Berlin. So that's me as a person. I'm looking forward to this symposium very much. Thank you.
Okay, so also warm welcome from my side. I'm Thomas Elsässer. I'm with the Max Born Institute here in Berlin. My field is ultrafast optics, spectroscopy, and also structure research. And it's my pleasure to chair this symposium now, I think, for the 4th time. And the format is kind of established, but I will just explain to you what we are planning for this morning. So the program has essentially 4 parts. We start with a session of longer talks, longer means 8 minutes, by the finalists of the physics competition. And then after the coffee break, we have next generation researchers with even shorter talks. And this is followed by a short panel discussion about astrophysical perspectives. And then after that, you are encouraged to approach our speakers. And to do this, we'll organize 3 speakers' corners, topical corners. You are free to choose the topic you want to have. And this is your opportunity to get in close touch with our speakers to discuss trends in the fields, in the respective field, to discuss challenges, and in particular also to discuss how younger scientists can be part of activities in this field and how they can integrate their research in the bigger framework. This is roughly what we plan for today. Okay, so let's get started with the finalized pitches, and our first speaker will be Henry Chapman from DAISY. His title is Observing Molecules in Action. Henry, please.
Okay, life, it turns out, is pretty complicated. Oops, is this working? It's not running. So most processes in life are driven by macromolecular machines, such as this one you see here. This is DNA polymerase, which is replicating DNA. And today, using AI programs such as AlphaFold, you can actually predict molecular structures, protein structures, from their genetic sequence. But these are static structures obtained essentially through measurements of crystals at cold temperatures. So to make movies like this, it's a lot of imagination, but also sort of seeing how these objects fit together. And what we'd really like to do is to really watch proteins and other macromolecules catalyze reactions and interact with the environment, and learn how to really design functional proteins. So to do that, we need good tools. Even the best optical microscope you can get can't see molecular detail because the wavelength is too long. So we need to lower that down to the size of the distances between atoms, and that's X-rays, also electrons. But the trouble with this is that this radiation is very energetic. It's ionizing and breaks bonds and essentially destroys the very sort of protein or structure that you're trying to see. So it's a little bit like being in a very dark room, kind of like this one, and having kind of a secret message on light-sensitive paper. So to read the message, we have to turn on the lights, but in doing so, it burns up the paper, so it's very light sensitive. So we can't read the message. So there are, of course, ways around this, and one way is to have a very nice high-end electron microscope and then put your protein in vitreous ice, so it's cooled down to cryogenic temperatures. And then you get these sort of ghostly images, limited by that radiation damage, essentially. But you can find the images that are of similar orientation and average those together and build up the structure. And this works really nice, and it's great. But again, it is cryogenic, so you can't watch dynamics, and even the act of cooling it down to these temperatures can change the structure. So X-rays are much more penetrating, and one thing you can do that, and has been done successfully, is that you can create large crystals, many billions of molecules, all arrayed in a periodic lattice. And when you shine X-rays on it, that they can interact with all those molecules, and the very weak scattering from each one of them can add up constructively in particular directions. And from these diffraction patterns, you can decode the structure. But now, again, you've got billions and billions of molecules, and it's hard to have them all acting in unison if you want to see dynamics. I mean, we can trigger with optical pulses, but even then, we can't get the optical pulse even through these very large proteins, crystals that are needed to sort of spread out that damage. So we've been looking at a third way to overcome the radiation damage problem, which is to use a fast flash, do flash photography. That way we can read our message, we can take a picture of the message before it burns up, and then sort of look at it as we like. So how fast a flash do we need? Essentially femtoseconds, because that's the time scale for atoms to move. And that's about 1 billion times faster than this picture taken here of a microsecond flash that's stopped this speeding bullet. So our big flash bulb is the European XFEL that was just mentioned. So this is a long accelerator. We need to create extremely energetic pulses that are compressed down to femtosecond duration. So it starts at DAISY and goes all the way into the next state of Schleswig-Holstein. So it's a big machine, big facility, and with that we can record diffraction from small objects that we're just streaming across the beam, constantly refreshing and collecting that data. We started out with sort of tiny nanocrystals of proteins, and we call this method serial crystallography. And with this, we can also trigger reactions with an optical pulse moments before the X-ray pulse comes along. And with that, we were able to watch a particular protein repairing UV damaged DNA. So you see here on the left there, it's DNA, a short strand of double-stranded DNA, which has been UV damaged. So two of the bases have sort of fused together. This protein photolyase recognizes that and repairs it. And what's interesting is it itself is light driven. So light activates the chromophore, this FAD, and which donates an electron. And we can, by doing this serial crystallography, we see that within 3 picoseconds after the flash, there's this conformational change that stabilizes the excited state, so that the electron has time to go and break these two bonds sequentially that are fusing the two nuclear bases. Then the electron is returned, triggering conformational changes that essentially eject those two nuclear bases, so that they can go and bind across as they should to their pairs. And that shows just how effectively and so how quickly this DNA repair mechanism actually works, and explains how that happens. But again, we're having to trigger all these molecules together in synchrony. Even in a small crystal, it's not clear if they all go follow the same reaction pathway. So we want to do this really molecule by molecule. Look at single molecules. And with the X-ray free electron laser, when we focus the beam down to extremely small dimensions, we get very strong, intense beams and we can actually measure diffraction from single molecules, as shown on the left there. And again, using these averaging schemes from cryo-electron microscopy, we can build up class averages of diffraction patterns, and then build up a three-dimensional sort of representation in Fourier space of the molecule, and then reconstruct the structure that you see there on the right compared to the known crystal structure. It's still pretty low resolution today. This is fairly new data. But so we're kind of like where electron microscopy was maybe 30 or 40 years ago. But we're very excited about this, and it's very encouraging because now we'll be able to sort of piece together the reaction. We can sort of really take one molecule at a time, figure out how it relates to others in the sequence of, and really see how molecules are functioning and how they function, and learn how to design new functioning proteins. So thanks.
Thank you, Henry, for this nice overview. Are there questions? Here.
Thank you very much. Really nice talk. I would have a question on the right image shown here on this donut-like structure. The DNA strands are visible on the surface of this donut-like structure. Is it also possible to visualize the internal structure as well?
Yeah, certainly. So we get a full volumetric image. So it's a thread, so we've captured the molecule in all orientations, so we can piece that together. I didn't mention that this is a heme complex from worms. It's quite a large thing, but we can cut it through, and we do see some variations in there. And the idea is that this heme complex has some dynamics that happen in the way the components are arranged, and we hope to be able to sort of capture that.
Okay, we have time for one more question. Maybe I can ask a quick one. Can you integrate water molecules in the crystals? Because the native environment of the DNA is, of course, aqueous.
Right, that's right. So currently we're sort of aerosolizing these molecules, as shown here. And what we'd really like to do is keep them in an aqueous environment. So people are developing these very ultra-thin liquid sheets, jets, that are only tens of nanometers. There's actually a lot of work been going on at SLAC on that. So if we can keep them in that environment, the water will add some sort of background, and so we've got to deal with that. But I think that's the way to go.
Okay, thank you.
Thanks.
Also, thanks again. Our next speaker is Claudio Emma from SLAC. And the title of his talk is Intense Particle Beams. Claudio, please.
Okay, so good morning, everyone. It's really an honor for me to be here among so many illustrious colleagues to present the work that we did this year on making the world's most intense ever electron beam. So I just wanted to start by giving kind of a quick overview of the context for those of you who are not particle beam physicists by trade. So particle beams are really unique tools for discovery and fundamentally very powerful probes of the natural world. So if you look historically over time at the amount of discoveries that have been enabled by particle beams, they are really now becoming ubiquitous technology we use everywhere in our daily lives. So starting from the 1890s, the discovery of the X-ray, going with more intense beams to the discovery of the nucleus, and then on, marching through the decades, all the way towards completing the standard model of particle physics with the discovery of the Higgs boson at CERN. So what you can see is that there's one through line here. The beams get more and more intense. The more intense they get, the more we can see deeply into fundamental processes in nature. And of course, particle beams started as tools for fundamental physics discovery, but nowadays, if you look at applications, they're everywhere from hospitals to, for example, imaging, as we just heard in this talk. Everybody sees the COVID virus here imaged at synchrotron facilities. And then even looking at things like historical artifacts, so you can use particle beams to look at scrolls by scattering, for example, light off of different kinds of inks and read where you could not. So they're really fantastic tools for discovery, but what is exactly special about intense particle beams, and who are the users that want more intensity today? So obviously don't have time to go into detail with all these applications, but I wanted to give you a flavor of the breadth. So there are many communities right now that are looking at the particle sources out there and saying, well, we want more intensity. And what does more intensity mean? It just means more particles packed into a smaller volume and compressed to shorter time duration. So just to give some highlights, there are new collider concepts out there that want to look at boiling the quantum vacuum. They want to look at quantum electrodynamics in this non-perturbative limit. So we have theories for what goes on there, but we really don't have any experimental way to access this regime right now. Having more intense particle beams would enable that. There are concepts for attosecond light sources to go even shorter than the pulses we can make today, to tens of attoseconds. This would allow us to basically have the world's fastest camera and resolve the motion of electrons in atoms on their natural timescale. Incredibly powerful. The list goes on: laboratory astrophysics, strong field QED. I just want to mention one that's near and dear to my heart. So intense particle beams can be used as drivers for advanced particle accelerators. So you can imagine taking a beam, colliding it with a plasma source, and exciting a large amplitude plasma wave. In this large amplitude plasma wave, the fields are just enormous. And you can use these fields to accelerate a second particle beam in just a fraction of the distance of what you can do with conventional technology. So this could really revolutionize both high-energy colliders in the future, but also just democratize access to particle beams, making a lot more university-sized accelerators feasible in the future. So then comes the challenges. So I guess, why don't we have these beams today in the lab? Is it just that we're bad at our jobs and we can't make them intense enough? Well, the answer is not really. It's really difficult to compress particle beams. And I tried to summarize that in the cartoon on the top of the slide. So the conventional paradigm for compressing particle beams involves using this sort of trick that I'm illustrating here in the top cartoon. So you start with a bunch, say it's many, many electrons, and you accelerate this bunch, but don't give all the electrons the same energy. So you give it this time-energy correlation. So the electrons at the back have slightly higher energy than the ones at the front. Now you send this beam through an array of magnets, and because the Lorentz force bends the particles differently, the high-energy electrons get bent less than the low-energy ones, and so the high-energy ones catch up. And in the end, you end up with a compressed bunch. So this paradigm works great, and it's used at many facilities, XFELs all around the world. But as you start to increase the number of particles in this bunch, the particles will radiate as they bend through the magnets. And this radiation will actually act back on the electron beam, spoiling the beam quality, diffusing it. So you end up with this kind of beam that looks like a snot ball, which is illustrated on the right. And you can't use this for applications. So that's the first challenge you have to overcome. The second challenge is that suppose you can make these very intense beams. Now, how do you measure them? Well, typically, we take beams, and to measure where they are, how big they are, we collide them with solid or gas targets. But usually, when you collide beams with targets, they don't do this stuff at the bottom. They don't turn it into Swiss cheese or drill holes in it. When the beams become intense enough, this happens. So you have to fix this problem. So we had these two challenges that we wanted to overcome, and we did an experiment at SLAC where we tried to make the world's most intense beams by doing things slightly differently. So the first thing we did is we, instead of using the radio frequency cavities to modulate the chirp on the entire bunch, we use a laser to impart a very, very localized modulated energy inside the beam. So the reason that lasers are good is that they enable you to control the chirp. You can get a very large amplitude chirp. You can also only put it over a small subsection of the beam, so you can really shape the longitudinal phase space. This means you get more compression with less bending. And that, in turn, makes it so that you can turn this energy modulation into a very large density modulation, in this case, for those of you in the field, with about 100 kiloamps of peak current and 10 GeV. So that's a petawatt of peak power. Now, of course, that maybe sounds impressive to some people, but then you have to measure it. And in order to measure it, as I said, we couldn't directly use conventional diagnostics, so we used non-destructive methods. In this case, we looked at the radiation of the beam after it had been fully compressed right before it entered our beam dump. We were able to use spectroscopy to back-calculate, using the radiated spectrum, what the bunch length needed to be. So this was great. We were very excited about this result. But most exciting of all is that we've already started delivering these beams to users. So as soon as the users at our facility got wind that we were making 100 kiloamp bunches, they said, OK, we have some ideas. And most of all, we've been doing plasma wake field experiments, looking at different regimes of plasma acceleration with these beams. So OK, I think at this point, we're at the stage where, in the talk, where we're patting ourselves on the back, maybe, and we're saying, OK, we have very intense beams. That's great, but what's really next? So if you look at the roadmap for accelerator and beam physics and the applications that I was discussing earlier, they demand ever more increasing intensity, some of them more demanding than others. For example, for the collider, 100 kiloamps is not enough. You want maybe 1 megaamp. So we need another factor of 10. And this, of course, has been recognized by the accelerator community, so much so that, at least in the US, a roadmap was published a few years ago, which in its decadal vision listed this as one of the 4 grand challenges for accelerator and beam physics. So we wanted to get to 100 kiloamps in the first 5 years. We can check that off. And now we want to go to a megaamp in the next 5. The good news is that we have some ideas for how to do that. It's going to require completely reshaping the technology once again. So not using lasers to compress the beam, but actually using plasmas. But of course, I don't have time in this talk to go over this, and we don't have any results, but maybe at the next Falling Walls conference, we can talk about megaamp beams. So with that, I just want to close. I have 4 seconds, so I can at least thank my collaborators, especially these 3 of my colleagues who were really instrumental in the experiment, and also thank our funding agency, the DOE, for supporting this research, and thank you for your attention.
Thanks, Claudio. Are there questions, comments? It's hard to see. Yes, please.
Thank you for the great talk. In the beginning, you mentioned the application for quantum materials. Can you maybe comment what the motivation there is?
Yeah, so essentially, with very intense beams, you have a sort of relativistic hammer. And now when you make the bunches short enough, you can basically excite quantum processes in materials. You can look at damage on extremely fast timescales. Now, the really exciting thing is if you sort of pair it with what was discussed in the previous talk. So now you have the beam, which can be the pump, and then you can use that same beam to generate photons to probe. And now you have a system which is kind of jitter-free because you generate the photons and the pumping with the same beam. So this is the kind of experiment we want to do. So going forward, yeah.
Okay. Yeah, I don't see any other questions. Thanks again, Claudio. And our next speaker will be Martin Harmer from Lehigh University, and he will speak about 100 years of superalloys. Martin, please.
Thank you very much. There are thousands of alloys, metal alloys, but very few that can survive extreme conditions of very high temperatures and very high stresses. Like, for example, the hot turbine blades in your aircraft engine, like the one shown here. And we give those that can survive the name of superalloys. They're like the superheroes of all the metals out there. The most successful example of a superalloy is based on nickel. Nickel superalloys are the sort of gold standard of superalloys. So let me tell you a little bit about nickel superalloys and then the alloys that we've made to talk about today. So nickel superalloys have evolved over many, many years from being polycrystalline, multigrain, which you see on the left in the figure, to single crystals on the right. Single crystals have much better creep resistance. Creep is the deformation of a material at high temperature. With time under load, it's like the ability to maintain its shape. And so we sacrifice some strength, which you get higher strengths with polycrystal materials, to get better creep resistance. That's a very major property of these materials. The main source of strength in a superalloy, a nickel superalloy, is this. In metallurgy, it's a very famous phase. It's called gamma prime. It's an ordered intermetallic alloy of nickel-3 aluminum. And the picture on the left shows this blocky structure it has. It strengthens the material, and the key to the strengthening mechanism is that it aligns itself coherently, so the atoms align from the matrix. You can see in the picture on the right, they align with that ordered intermetallic gamma prime phase. So it's a very important phase in the development of superalloys in these applications. So now, in terms of what we've done, we've taken the opposite approach to single crystals. So if you can imagine now taking the opposite approach and asking, what can we do if we make the crystalline size of a polycrystal as small as we possibly can, and we build the structure atom by atom in such a way that we can get both high creep resistance and very high strength. And this is just the kind of essence of the things that Richard Feynman talked about in his very famous lecture in 1959, which you probably have all read. There's plenty of room at the bottom. So we've sort of taken some of that advice from predictions, from prophecies from his work. And I would mention too, he did emphasize in his lecture the potential importance of layers and layer structures and building atom structures from layers. So here's what we've done in this work. Although let me first just point out that it was 40 years after Feynman's lecture that electron microscopes became good enough to actually see the atoms to be able to do the things that he talked about. The discoveries that we've made in looking at the individual atoms, shown in this figure here, have shown us that the spaces between the grains in polycrystal materials form very unique, distinct layer-like structures. We actually call those, the term that we use for that is complexions. And these form different layer structures, and depending on the nature of the layer and the bonding in the layer and the number of layers, it can completely determine the properties of the material. So that the difference between one layer and two can be the difference between a brittle material and a ductile material. It can mean the difference between a material that doesn't creep and a material that falls to pieces. It can make a massive difference. So complexion engineering is something that we have now become very aware of in the field of material science and engineering. So in the materials that we've developed, we've collaborated with Chris Darling's group at the Army Research Lab to make a superalloy from nanocrystalline copper. Copper is probably the last material you'd pick to think of making a super alloy out of. It's soft even at room temperature, and the nanocrystalline grains in pure copper are very unstable. They'll grow at room temperature. So we've done this in a very special way, processing way to make this material. We've alloyed it with tantalum, and made it, tantalum is insoluble in copper, and we've milled it at very high energy at cryogenic temperatures to dissolve mechanically the tantalum into the copper, then annealed it, heat treated it, and it precipitates out a nanocrystalline structure and these really tiny precipitates and nanoclusters, only a few nanometers of tantalum. And it does a pretty good job at pinning the structure, stabilizing it, and giving you reasonable properties. It's a very good start in the alloy development. But there is some oxidation of the tantalum, and there's some growth of the particles, so it's not ideal. So we further modified this composition to add lithium, particularly as well because it prevents the oxidation. Lithium is a very strong reducing agent. And it produced an incredible transformation in the microstructure of the material. So we see an atomic resolution image now of what happens when you further add the lithium. So in the image in the middle of that particle, that precipitate phase there, you can see it's sort of bluish regions. It is reacting with the copper to form Cu3Li, which is gamma prime, which is why I mentioned it earlier. So gamma prime forms as the phase, and the energy between the gamma prime phase and the copper matrix is high, and to lower that energy, it forms a complexion at the interface, which is a bilayer of the tantalum. So it's like it's enclosed, safe almost, as it were, where it's encapsulating that phase of Cu3Li. The properties of this material are quite amazing. So this material can be, first of all, its creep resistance is very comparable to nickel superalloys. Very comparable. It's about 6 orders of magnitude or more higher than the creep resistance of copper without the tantalum lithium. Its strength is about 1,000 megapascals, which is the order of the strength of many steels. And the real benefit of this material is the stability of it. The Achilles heel of nanostructured materials is that they're not stable. This material we heated for 10,000 hours, which is over a year, at 800 C, which is close to the melting point, and the strength dropped by just 4%, still at 1,000 megapascals, and the grains grew only 1 atom spacing every 100 hours. So it's incredibly stabilized. So we're very happy with the results of that superalloy. So we feel that in the future this is paving the way to make perhaps other superalloys of what we'd call unobtainable materials now. And the key to this work was the complexion that formed, the bilayer complexion. So we think complexion engineering can pave the way to make other new materials that have unique combinations of properties. And I would like to end with the acknowledgement of the team effort that put this together. We worked with the Army Research Lab. We worked with Louisiana State University group and Arizona State and various people at Lehigh. Thank you for your attention.
Thank you, Martin. Are there questions?
Sorry, I may have missed it, but how complicated and how expensive is it actually to manufacture this material?
Well, that's a great question, because I think that also is the future. It requires a different kind of manufacturing than is traditionally used, because it's powder consolidation at low temperatures, and the material requires, at the moment, techniques like high pressure torsion or high pressure extrusion processes to make the material. So it will need some modification and adaptation. But you saw from the part in the hands of the metallurgist Chris Darling's group, it was pretty big. So that the ARL have demonstrated you can make much larger, large bulk components out of this material. But it will need some, I think the manufacturing science will be an area of much need. But there's every reason to think that it will be feasible to make large components.
Okay, there was another question over here.
Yeah, thanks. I'm curious to know the modifications that you make to the copper change its mechanical properties. Does it also affect the electrical conductivity?
Absolutely. Actually, I forgot to mention that was a major point. The major point is that the reason we picked copper was because of its higher, actually, thermal conductivity, because thermal management is the key. Most of the developments in the field of superalloys, especially for aircraft engine, have come through advanced cooling methods. I mean, I don't know if you know it, but the temperature in the combustion chamber is higher than the melting point of the alloy. So if you didn't have that, you'll never fly again if you hear all this. But if you didn't have that, literally it would melt. So it's 4 times higher, the thermal conductivity. So one of the advantages might be things like high temperature heat exchangers. Any situation where you've got thermal management, the copper brings some enormous advantages. So thank you for asking that question.
Okay, I think we have to move on. Thanks again. And our next speaker is Tanja Mehlstäubler from the Physikalisch-Technische Bundesanstalt in Braunschweig, and she will talk about time and frequency standards and probably atomic clocks.
Yes, thank you very much. Indeed. Yes, and I would like to bring you back to the time of 1967. That was a new definition of the second was established then. And it was actually the first time in thousands of years that we went away from an astronomical timescale to a quantum timescale. So we use now for the very first time a quantum system as a natural pendulum, and that is the resonance frequency between 2 quantum states to define a timescale and to define a second. So the cesium atom was chosen back then, cesium-133, and that is the resonance frequency of the hyperfine states in the ground state. So this is what we take as a current definition of the second. And this cesium clocks has improved by orders of magnitudes back then, and they're omnipresent in our daily life. You can't imagine how everywhere there are basically clocks making your everyday's life, in telecommunication, in financial transactions at the stock market, in the navigation system, on mobile phones. Even in the future, quantum communication will highly profit from clocks because you need also good time taking to correlate the entangled photons. Now in the 1990s, a new type of clock showed up. We call them optical clocks. So they follow the same concept, but you go a level of energy higher. So that means the resonance frequency we're interrogating is much faster. It's actually 10 to the 5 times faster than the microwave, the cesium clocks. And you can imagine it makes just a much finer scale to measure time. And that's why we can measure them more precise and faster. And so it's not surprising, as you see here, these optical clocks, meanwhile, have overtaken the cesium clocks by almost a factor 100 in the laboratory. So the BIPM established a roadmap how we can potentially now redefine the second based on these optical clocks in the future. However, there's a caveat. There's a lot of criteria still missing to reach this fulfillment and to establish a new second. And I will come back to that in a minute. So, but first I would like to show you some modern applications of this high level of atomic clocks. There are plenty of them again, and for sure we will see them in communication, telecommunication, even 6G and beyond will require definitely in high bandwidth optical frequency standards. But I would like to actually go in here now in 2 types of applications that are a little bit less known maybe. So we're having our quantum system to measure time. And if I measure time, I enter the realm of general relativity, of Einstein's domain. And I think that's highly interesting because I think there will be a lot to be discovered in the future when we measure quantum time, or tests of general relativity, because these 2 theories don't really match well. They don't fit quantum mechanics and relativity. So what we have done in our lab, we've basically established a new type of Michelson-Morley experiment measuring the isotropy of space. And at the moment, we hold a record of 10 to the minus 21 that Einstein is indeed right. So local Lorentz invariance still holds. And what we replace, basically the old laser interferometer with the modern atomic matter wave interferometer and using the electronic quantum states to measure the isotropy of space at this incredible level. We also used a high-precision spectroscopy in our atoms to do nuclear physics. We can use the electron as a sensor of the nucleus and see how the nuclear shape is changing. When just another neutron arrives from isotope to isotope, we can see in our measurements that the nucleus is deforming and changing by a few femtometers. And then in collaboration with high energy physics, nuclear physics, astrophysics, we can set new bounds for possible new particles, fifth forces, looking for dark matter. So that was also a recent outcome of this year. Then back to the ground, we're engaging ourselves now in geodesy. You see the geoid, this knödel in the background. So again, we're using general relativity, so gravitational time dilation. There's a nice Bloomberg video if you're interested in that. Time dilation tells you that time is ticking slower at your toes than it's ticking around your nose level if you're standing. And this I can resolve with 1 centimeter precision. My clock with 10 to minus 18 can resolve time differences of just 1 centimeter height level. So we teamed up with geodesists to monitor the world. Yeah, we know climate change is not only melting the glaciers, it's also subsidizing the mountains. The permafrost is diminishing. The Zugspitze is probably shrinking by 1 or 2 centimeters per year, but that was not detectable with classical sensors so far. Now, how do we reach this incredible level? We're using a quantum system that is the most precise quantum system we can have nowadays, only limited by Heisenberg's uncertainty principle, a trapped ion. These are very good clocks, but there's a fundamental problem that they're limited by quantum noise. So if I want to resolve the 10 to minus 18 or even 19, it takes 100 days to reach this. So the projected accuracy is limited by the feasibility to measure it, to resolve it, so noise. And how can we push that? And that's where our proposal came in more than 10 years ago, to scale up quantum systems for time and frequency measurement, for metrology. Not for quantum computation, but to use them for accurate time and frequency measurements. And it was incredibly hard to convince people that this could work. I was very surprised, so I started with a junior research group back then. And there were many worries on one side, but we found solutions on the other side. In particular, we demonstrated that a self-organized crystal and system always organizes itself that the electric field must be zero, because it's stationary, it's not moving. So we don't have first-order time shifts. We built our own ion traps. We studied the complex system of many particle dynamics, heat transport, and how we can cool that. So many things. In particular, I would like to show you here the ion traps that we developed ourselves at PTB. Now we teamed also up with Infineon to bring them on an industry level. These are the beautiful Coulomb crystals that we have. These are terbium ions, where you see fluorescing in the light of the laser. And we measure time gradients. We can resolve time gradients and verify that time gradients in our crystals are below 10 to minus 19. So we can make a complex Coulomb system very homogeneous for time measurement. And then after 3 years of evaluating the clock, because if I tell you this is 10 to minus 18, you probably will not believe, so I have to compare clocks. We did this for over 3 years, and actually it was surprising. It was a world record at first shot. So for the first time, our clock fulfilled this mandatory criterion for the redefinition of the second, that we measured time and frequency at the level of 4 times 10 to minus 18 in direct clock comparisons. So that not only made it to the cover of PRL, but had a big impact in the press and so, because it was so important for the potential new definition for the second. So, and for us, of course, it's very important because it was the benchmark. This new concept of a multi-ion clock, of a crystal clock, really works, and we are more than competitive with standard optical clocks. So this is then the future view, what we will do with this new type of multi-ion clocks. We'll go on scale with integrated photonics to bring them up on the mountain for geodesy and many other applications. But this is the very future vision with integrated ion traps, where we work now a lot with industry partners. And yeah, with this I'm actually a little bit faster than I thought. I'm very happy and looking forward for your questions. Thank you.
Thank you, Tanya, for this fascinating talk. Are there questions?
You've shown this exponential plot of accuracy over the years. How long is that going to continue into the future?
That's an interesting question. Actually, maybe it depends on the interpretation of the viewer, but you might see a leveling off when you look at the zoom up here. So you see the cesium clocks are already leveling out, the 10 to minus 16. This is fundamental. This is collisional shifts. Yeah, it depends now on the interpretation if you see the same effect happening here at the optical clocks around 10 to minus 18. I'm pretty sure we will make it down to 10 to minus 19. There's already like a clear path. We already published a paper in 2019 how we can reach the 10 to minus 19. You always can estimate the error budget and say, I have to do this. I have to cool further from millikelvin to microkelvin. We know how to do it. So I think 10 to minus 19 is reachable. Then we don't know. Then this is like looking in the glass bowl. What other new effects we will discover. Every time I measure more precisely, I'm surprised what I discover. Even the established methods of how to measure the tiny micromotion of these crystals, when we measured it precisely, we discovered that the old model was wrong and we had to refine it. So I don't want to predict the future. What I should say, there's a difference of absolute accuracy and repeatability and precision. This is sometimes confusing because sometimes you might be here limited in absolute accuracy by the unknown of a natural constant, which is constant. And if you measure time, you always get the same reproducible result. And you can use it for quantum sensing, you can use it for a flywheel, for telecommunication, for anything. But you will never know the precise absolute value because you don't know the natural constant. So we have to be careful about what is an absolute claim. The absolute claim will always be higher than the relative measurement. And for many applications, it can go down even to the 10 to minus 21, I would say.
Okay.
Sorry for a long answer.
A quick one, please, over there.
Thank you very much. It's fantastic. There is now the discovery of that transition of a nucleus of about 8 electron volts, so going again to a higher energy scale. And people say because the nucleus is a much less disturbed object than the atomic shell of an atom. What is your take? What is your prediction? How far can, say, this kind of clocks go? It's also an optical clock in some sense. How does it? Can that break the 10 to the minus 18, 19 barrier and go even deeper? Because you mentioned the stability of fundamental constants. That is also a field of interest. Whether our constants are really constant with time, because it would change our view of the evolution of the universe in some sense.
Yes, I mean, these are many questions in one.
There will be speaker's corner.
Maybe in general, in a snapshot, so thorium is ticking at 148 nanometer. Our clock is ticking at 230 nanometer. So this is not like an order of magnitude, that's a few 10%. So this is not a huge lever, yeah. Where thorium, as you mentioned, is less sensitive to external field because it's a compact nucleus, so the absolute accuracy could go down further. However, there's also a caveat because our clocks at the moment are really limited by a lot of other noise problems, and in particular time dilation. If the particle is moving, yeah, even at microkelvin temperatures, you do get motional time dilation. Yeah? And this is the same for any clock, also for a nuclear clock. So when we're cooling, and if you're cooling a thorium crystal to the millikelvin, you're limited at 10 to minus 18. So there's a very complex question that you raised, and I'm happy to discuss that in a corner. But it's not black and white, so they will have to deal with all the other systematics that we also have.
Okay, thank you. Thank you. Okay, we now move on to the final talk of this session, which will be presented by Richard Norty from Delft University of Technology. His title is Breaking the Wall of Miniaturization in Nanotechnology. Please.
Yep, thanks for this invitation. Today I want to talk about some research we've been doing in our labs. And for decades, usually the question is how small can we make nanotechnology? And one of the questions we've been asking is how big can we make it? And so one way to answer why this is actually an important question, we can look 65 years before when this age of the space exploration. So this shows you more or less all the different space missions we've done over the last 65 years since we started going out into space, a few to Mars, a few to the moon. And if you look out even further, you'll see that there is a handful of human-made objects that have made it out to deeper space, to the outer planets. But if we look on a sort of cosmic kind of scale, we really haven't gone anywhere. We sent Voyager 1 out in 1977, and we just barely left the solar system. And so if you start looking at how long it would take us to get to the nearest star, with any kind of existing propulsion systems, you're talking about 10,000 years to get there, just to the nearest star. And so in 2016, basically thousands of scientists kind of coalesced around a bold idea. And the idea was to use decades of nanotechnology to make, nanotechnology advancements to make microchip satellites. The idea being that we could attach them to large sails, lightweight probe. And the idea being that if we get this small probe with cameras and communication systems and attach it to a large sail that is about 1 gram so about meters in size and nanoscale thickness, that we could, with 10 minutes of laser exposure, accelerate these sails to about 1/5 of the speed of light. And this would essentially reduce our times down from 10,000 years to something about 20 years, about, let's say, a generation. And it's a really, I would say, crazy idea when I first saw this proposal, but it definitely got me thinking about what is possible with nanotechnology we have today. But one of the things that people realize is that the light sail is actually one of the hardest components to make. And why is that? Well, if you look at the chip really requires making everything smaller in X, Y, and Z. And that's something we've been doing for nearly half a century. But the sail is a really different component. It's a really different challenge. It's the only nanoscale component that needs to be scaled out to meter scales, right? And that makes it very different from any kind of nanotechnology that we've been doing over the last 50 years. Right now, our lab is really looking at not just propulsion, but how can we use these things for optical computing, for extreme sensing, where they basically where mirrors are really quite important. Okay, so state of the art, what was actually done when this thing was announced? What was possible? Basically, I would say one of the best materials you can get is thin films of ceramic, which are about 1,000 times thinner than a human hair. And counterintuitively, you would puncture it with holes to make it reflective. So it would basically be reflective at a single wavelength, which is perfect for lasers. It also makes it lightweight if you can remove half the weight with holes. And so basically when it was announced, what we saw is that basically the biggest types of materials, these photonic crystal reflectors, were about fractions of a millimeter size. And so now in our lab, what we've been doing is thinking about so this basically gives you a sense of what those look like. About 300 micron by 300 micron reflectors is what was possible. And now we've been really thinking about the physics of how we manufacture these things. And so here gives you a sense of kind of a comparison. So now we can make these things 60,000 times larger up to the wafer scale. So something that you can really hold in your hand and look at. And this basically essentially gives you some of the thinnest mirrors that you can possibly make. Okay, and so one of the things that now we're looking at in our lab is how to actually show that these things can work. So now what we're doing is we're getting away from this idea of manufacturing something and then taking it into the lab. We're trying to meld these two concepts together. And so now what we're doing is we're actually, for here you can see a wafer. We put it into our machine. We can actually fabricate it, send it into a chamber where we have high-powered lasers. And the idea is to essentially lift these objects stably and lift objects that are about 100,000 times larger than anything that's been levitated with coherent light. So these are really large objects that you can use for sensing, to also kind of look at the dynamics, light-matter interactions. So you can kind of think of it as a rocket that you've chained down, you've fired it up, and just to see the dynamics, just to see how this actually works. Okay, but what can we actually do with what we have today? Because we're not making meter-scaled light sails. This is not, I think this is actually a really hard challenge. But here, just to show you, these are all the fastest flyby probes to every planet in the solar system so far. The fastest we've ever gotten to Mars is about 4 months. To Saturn, it's about 7 years with Cassini. And Voyager, which has taken about 46 years to get to the edge of the solar system. And so if you take the mirrors we have right now, the reflectors that we have right now, and with about 1,000 times less laser power, we can actually bring these times down quite a bit if you want to take still a 1 gram payload. So the idea being that we can now, for instance, think about sending microchips to Mars in about 32 hours. So about kind of the same way that you send international mail. The other one really nice idea is, for instance, being able to send microchips as you like to Saturn's moons where there's supposedly oceans, about sending one there in less than a month. And the idea of getting to, for instance, to Voyager's position, which has taken us about 50 years, getting there in about 1 year. And that is, I think, incredibly interesting. Yeah, so I think these are big goals. I think you can develop a lot of nanotechnology with these big goals. And it's important to realize that, the first flight was in 1903, just a few feet above the ground there was a plane. And in about 66 years, we were landing on the moon, right? And this is a crazy short time scale. And so I am excited about, essentially this idea of hitting this wall, more or less set by Moore's law, and then what we can really do afterwards when we hit this wall. And I think going upwards is going to give some very interesting results. So thank you.
Thanks, Richard. Are there questions? There's a question.
Thank you. Great talk again. My question is, you probably have to fold the structures you are looking at to transport them to space at some point. Is it something you tried, to have these surfaces and to fold them and maybe?
So actually the idea of this system is more or less, in a way of being able to manufacture things, let's say in low Earth orbit. A lot of these systems actually work in vacuum. They'll have vacuums for free in space, which is great. But this is kind of the idea, is to pre-manufacture these structures in orbit, for instance.
There was a question here.
Yeah, thank you. Great idea. I'm just wondering, assuming that you can send such a chip into space or into the solar system, would it be able to send back any data?
Yeah, this is a really big question, I would say. No, it's a great question, and I would say there's really a whole team of scientists working on this communication system. But that's why, for me personally, I think these shorter missions are really very, very useful, and actually, I would say in some ways one of the more interesting prerequisites, because I think you'll learn a lot from these shorter missions. How do you send back something efficiently? Because Alpha Centauri is really quite a long ways away. Yeah.
Okay. Yeah.
Just a very short question. What are the estimates of the laser power you would need in order to accelerate these sails?
Yeah, so the idea being on the order of tens of gigawatts of power. Now in the lab, we've actually put about 1/10 of this onto our sails, and we're now figuring out that they actually can survive these laser powers. So one of the big challenges is can you make materials that can survive this and reflect this light, and that's something that we're now answering I think in a good way. But yeah, it's quite a lot of power.
There was a question in the back still.
Yes, thank you for the great talk. So concerning the communication with the system, can you maybe implement not only a sail, but also maybe like a meta surface on the structure? So maybe to have a kind of antenna then for sending signal back?
Yeah, and people have actually proposed this quite a bit, of using the sail itself. And the nice thing about it is that when you have something that's meters by meters, or these large scales, you're talking about trillions and trillions of holes, which means that you can actually functionalize different parts of it because you have so much space to design, which is very different from anything you can do with a nanoscale mirror. That's really something very different. Yeah.
Final one here, please.
Yeah, thank you. My question is, would you also be able to combine this sail with solar cells? Because somehow you need energy.
You could, but they're really different scales. So solar sails are incredibly impressive what they've done these days. So they can make things that are 7 microns thick and meters large. But what we're talking about here, this mass scale is very, very different. We're talking about something that's about order of magnitude smaller than, or 2 orders of magnitude smaller than a solar sail. So it's really the one. I mean, if you think about a euro coin is 7.5 grams. We're talking about something that's 4 by 4 meters that needs to be 1 gram. So this is really a nanoscale object. It's not even a micro scale object, a micro thickness object. So maybe it's possible. Sorry, to get to your question, but maybe it's possible to combine in the future. Yeah, could be, but I think they're very different weight scales.
Okay, then let's thank Richard and the other speakers of the session. There's enough time. And there will be enough time for discussion later in the morning. We are now having a coffee break until 10:30.
For our next session, which is the next generation researchers pitches, we will have 5 pitches, short pitches with a little bit of time for questions. And I'm really looking also forward to this session. And we will start with Mattia Cesaro with his first pitch. So please come and welcome you here.
Okay, so thank you. So let me start by asking you to imagine that you're falling inside a black hole. So of course you're doomed, but you might still be interested in thinking about what happens at the very center. And well, the short answer is that we don't know. And we don't know because the best description that we have of gravitational interaction, namely Einstein's theory of general relativity, breaks down in these extreme regimes, like the center of a black hole, or for example, the beginning of space and time, the Big Bang. And it is believed that only by correctly incorporating quantum mechanical effects, combining them with general relativity into a theory of quantum gravity, might provide us with the correct framework to address these questions. So my research takes place in the realm of quantum gravity theories. There are many candidate theories, none of which can claim success. I should be very honest with you. And in particular, I look at supergravity and string theory. You might be interested in asking, okay, but what can these theories actually tell us about these extreme regimes? And the answer lies in duality symmetries. So what is a duality? You're all familiar already with the wave-particle duality in quantum mechanics, and that's a very good start. But a good analogy, although a bit imperfect, could be trying to define yourself with a single word. That's a bit of a hard task, because of course you're a scientist, but you might be also at the same time a daughter or a son, and then a friend, and then you might like swimming, so you're a swimmer. So which one is the correct description? The answer is that they really all are correct descriptions of yourself, of an underlying concept which is yourself. And they're just highlighting different corners. Sometimes they look highly incompatible as well. Well, this is a duality in string theory. We have all these different string theories which look like very different theories at first sight, but they're all really related by this mathematical object called duality, and they form a larger fundamental theory that nobody knows very well what it is. And okay, I provided you with an analogy, but what a duality really is, I don't really have a pointer here, but it's this weird object here, which is a highly mathematical picture. I won't describe you what it is, because it's a bit long. But okay, so what we are looking at the moment is in this extreme regime of the Big Bang, as we go backwards in time, we're trying to understand what happens when the concept of time, of space itself starts to lose meaning, and in a sense it de-emerges, and something more fundamental takes its place. And let me tell you that this something more fundamental, or a candidate for this something more fundamental, might be precisely this, oh, beautiful if you ask me, abstract mathematical object. So in a sense, the answer to what replaces space once this loses meaning at the center of black holes or in the Big Bang might be symmetries. Thank you.
So we have time for one quick question. Yes, please.
Thank you. Do you change the meta content or the spectrum of your strings or something, or why do you say in there space is dissolving? So what is the symmetry about? Is it a space-time symmetry? Is it an internal symmetry? Or?
This is an excellent question. It's a very peculiar kind of symmetry. Somehow I use the word symmetry almost improperly, in a sense, because it's a very weird thing, right? Dualities are really symmetries between theories, not between objects of the theories. But at the end of the day, the things you measure are really the same. So they will provide you with the same answer. And if you're interested only in the things you measure experimentally, which I think is an important part of physics, then this is the concept of a duality symmetries. So in principle, these theories might look completely different as you're a scientist, you're a swimmer, and so on. But then you're really interested in the end in experiments and what you can actually measure. So it's a bit of a weird symmetry in this sense, I agree.
Okay. Thank you. So since the very short pitches, let's thank the speaker again. So I would like to welcome Anihita Kamari as the next pitcher.
We face with It's work? No? Okay. We face with several challenges this year. Cancers become more resistant. Food needs to be remain healthier, and battery lose efficiency. And soft biomaterials are not communicate with the body anymore. So we made a wall between the fields, and each field try to solve their problem behind their walls and by their own method. So, but lab works separately, atoms don't. So atoms actually move whatever in the lithium battery or in the cancer cell or in the protein food. So we can actually take the interdisciplinary atomic center view because each large-scale function starts from the small atomic motion. So by understanding the atomic motion and monitoring in the system, we can find the mechanism behind the phenomena. And after that, we can design highly performance molecule. So across the medical, biotechnology, food science, or energy, we can actually find the same atomic logic in the systems. Actually, I took this strategy to solve the project, look unrelated to each other. For example, we actually try to design allosteric drugs against the D-ubiquitin enzyme. Actually, we work on the manuscript now, designing the highly performance rechargeable batteries by monitoring and finding the mechanism, ion transport mechanism in the system, designing a more efficient therapeutic peptide for neurodegenerative disease by identifying the amyloidogenic region in the system and optimize the food protein, in this case, the casein in the whey proteins, by understanding the additive interaction in this system. And in general, we can say we can decode the structure-function relationship between the proteins, for the proteins, in many phenomena. And I think we can, for high efficient design for the molecule, we can start from atomic center view. That's it.
Thank you. Thank you very much. So do we have questions? So one question I had was, for example, is this a theoretical work or are you doing experiments?
Okay, that means what is the atomistic logic here? Mm-hmm. Actually, for these cases, I use the molecular dynamics simulation, and I try to keep it simple. I mean, like the classical, but in some of the case, I use some type of the molecular dynamics simulation. For example, I use the enhanced sampling method for some of them. But anyway, we can use the molecular dynamics simulation, and sometimes we can confirm them with the spectroscopic method for the, only confirmation, in my opinion. These two major.
Thank you. So let's thank again the speaker. Now I would like to welcome Aditya Tamar, our next speaker, to the platform.
All right. So in galaxies which have black holes that are billions of times the mass of our sun,
one of the consequences of them being really powerful accretors is that they have relativistic jets. And when these jets are along the line of sight to us, we call these sources blazars. Now, blazars in themselves are an incredibly interesting class of sources because they've been known to emit across the electromagnetic spectrum. So we're talking about 18 orders of magnitude in frequency, right from radio frequencies to the gamma rays. And so they're excellent laboratories for multi-wavelength astrophysics. Until recently, they got a little more interesting. And this is when neutrinos come into the picture. These subatomic particles, which have an exceptionally mature theory in the standard model, but they're at an equal stage of infancy when it comes to their astrophysical origins. So what ice cube observations, which is this observatory in the South Pole to detect neutrinos, showed that one of the origins for these astrophysical neutrinos could be blazars. And that was well and good, but then the question was that what is so interesting about these sources that they could be neutrino emitters? So just to show an example, the source that you see on your screen is a source PKS 1424-240. These are linear polarization radio frequency observations of the source that, by the way, have not been photoshopped. This is actual data at 15 gigahertz. And so here what you're doing is that you're looking into the jet cone of the black hole. So as you go towards the center, you're getting closer to the black hole, your polarization is increasing. So these kind of sources are the sources that I'm dealing with, where the viewing angle is really small, the polarization is extremely high, and they've been indicated that these might be the sources that are interesting for neutrinos. Now, the state of the art right now was that there were population-based statistical studies of what can be done with them. And they showed that these are the kind of sources that if they're radio bright, they're radio loud, they can be sources of neutrinos. And so where my research comes into play is I'm trying to use radio observations as an anchor to not just localize where the neutrino emission is coming from, but also understand the mechanisms that are driving this. So the questions that we're probing is, what is this Goldilocks zone of parameters of magnetic field strength, particle populations, that will not only give you consistency across the electromagnetic spectrum of the data that we already have, but also give you neutrino detections. And this has profound implications for understanding how magnetic fields are distributed in the jets, how are particles accelerated in the jets, and how this fits into the broader context of the next generation of multi-messenger astrophysics. Thank you.
So we have time for a question or two, depending on how long the answer is. Please go ahead.
Thank you very much. You mentioned the electromagnetic spectrum. So could you also get additional information from X-ray observations, although not at that resolution?
Yes. So in my day-to-day job of modeling, we look at archival data from radio, optical, infrared, X-ray, and gamma. And so we do something called the SED fitting, which is a spectral energy distribution where you map the flux versus the frequency. And so when you have a certain parameter space that you want to model, you'd like to be consistent with the data across previous frequencies as well. So that's one of the challenges that we have, because one of the greater difficulties is that how do you get one set of parameters that give you across the electromagnetic spectrum and gives you neutrinos? So yeah, we do indeed consider X-rays.
We have some more time for another question. So I have one. How many of these objects do you have where you can look down the beam which comes out of the, down the jet which comes out of the black hole?
About 20 of them.
Just 20?
Yes, as of now, as of last year.
Okay, yeah. Thank you. So thank you very much. So I would like to welcome Svetlana Vasileva, our next pitcher. Please.
Thank you very much. Hi everyone, let's talk about skull. This is also kind of the wall for our brain, the ultimate protection. But don't worry, I'm not here to break it. I'm eager to understand how and when it emerges. When we're just being born, we have a little squishy point over our head, which is called frontanel. It's full of stem cells. That's why it's so soft. It allows our brain to expand before bones fuse. And the timing of it is the most interesting part. It's not too late, not too early, perfect to protect while allowing stem growth. And we look at the section of the skull, we can see that it's multi-layered structure. Between bones, there is a special region which is called suture, which is full of stem cells. Exactly on the border between suture and bone lies the heart of my research. Here, stem cells understand whether to become bone or remain potent. If you look on the sample from the top, using microscopy, you can see two main characters of my research, nuclei and collagen. Nuclei show me where the cells are, and collagen is representing extracellular matrix, the scaffold that transmits mechanical cues. If you look at the system long enough, it starts looking back, and you can see the clusters that cells are forming, with no collagen between and really dense structure surrounding them. To capture it more precisely, I developed a computational tool which can extract the intersection masks, special region where cells meet or share boundaries. With this analytical tool, I'm trying to reintroduce the poorly understood concepts such as mesenchymal stem cell polarity, comparing cell-cell interaction and cell-ECM interaction. I also can understand how cells align or collectively react to physical environment. Then I can tune this mechanical condition a bit with releasing of tension or applying stress. And here, more and more questions arise. For example, we can see changes in nuclear shapes and also shapes of collagen network. One of the examples is changing of lattice from triangular to circular. And one of the questions is, what would make triangles become circles? And this is the question that I'm working at right now. Through these images, I'm trying to understand the hidden language of shapes, how this organization can encode mechanics, and how mechanics guides this balance between protection and health development. So skull is not just a barrier, it's a live and adaptive system that can show us how nature emerges and shows the precision and patience. Thank you.
Thank you. Questions? Please.
Great research, I love it. My question is, could this be used in the future for people who suffer from bone cancer to reconstruct these bone structures?
Well, this research is actually aimed on the diseases with problems of nuclear cell shape and exactly for proteins on nuclear envelope. So, for example, laminopathies would be the decision, not the cancer, because in cancer it's definitely much more complicated than mechanics. And when we talk about diseases with problems with mechanical output of the system, then it could help.
Okay. Other question? Yes, please.
Thank you. So often in nature, shapes arrange in order to maximize efficiency and minimize energy. Have you looked at some minimization procedures of, for example, free chemical energy and things like that?
No, we actually not really able to check the energy. In terms of shapes, it would be analog of taking less space than more, and then it would be maybe more efficient for cells, especially inside the cluster. But we cannot prove it experimentally, but it's actually a lot of fun because you can play with game theory with it, or actually trying to understand what is the contact number for the cluster, or which minimal area it can cover, and then align it theoretically with energy. But we don't do that yet.
Thank you very much. So I would like to welcome Joppe Witstam, our next speech.
Thank you for the introduction. In these times of large language models and AI chatbots, people tend to forget that we're actually in the second AI craze of the past decade. 10 years ago was the first time a machine beat a human professional in the board game of Go. Shortly after, that machine, AlphaGo, played Lee Sedol, at the time one of the best Go players in the world. AlphaGo won the game 4-1. Lee Sedol is the only human that ever beat AlphaGo. In a few short months, machine learning went from never beating human professionals to never losing. Now Go is just a board game, and today's ambition is artificial general intelligence, machines that act competently in any setting. If these systems surpass human capability in practically any domain, it will be dangerous if we are not able to steer these systems towards goals that we intend them to pursue. This problem might best be explained as an analogy to evolution. Evolution and machine learning are both optimization processes that produces intelligence, humans, and learned models, respectively. These intelligences are themselves able to optimize for goals. The goals that these intelligences optimize for, they are instilled by machine learning and evolution, but only approximately mimicking the goals of evolution and machine learning. Just as humans started pursuing goals that are at odds with the goal of reproductive success, for example, by the invention of contraceptives, learned models are expected to pose a threat to the goals that we try to instill in them. Currently, leading AI labs are trying to create increasingly autonomous and agentic systems based on large language models embedded in increasingly complex environments. My research is motivated by the need to understand the safety implications of these systems. This requires an interdisciplinary effort from computer scientists, cognitive scientists, physicists, and maybe even social scientists and philosophers. And I urge leaders of science and funding bodies to facilitate this research to safeguard the future of humanity. Thank you.
So I already see one hand risen.
It's obviously a super critical question. Philip Gerbach from Venture Labs. It's obviously a super critical question. It's funny because I used this example 10,000s of times to say what makes you optimistic, or what approach can you even think of to think you might be able to align a superior intelligence, right? I think the reproduction is a perfect example, right?
It might be impossible. Yeah, you might be very pessimistic. Yeah. I try to be optimistic in the goal of actually making these systems safe, but you might be right. It might be impossible.
Another comment or question? Yes, please.
Yes. Do you think that unless the intelligence has some kind of embodiment in the physical world, that it actually can pose any kind of a threat? Because can a set of virtual intelligences understand enough of the consequences of trying to turn itself off if it's not physically embodied?
Yeah, actually, I do think that embodiment is required. I think that large language models, the words that they are manipulating, they are not grounded in our world. But I think that the direction that AI labs are taking, they are training it in more embodied modality, and I think that this is a worrisome direction.
Okay, thank you very much I would like to thank all the speakers, and we will be now moving to our next session, which is on astrophysical perspectives with Chimio Janvier and Brian Schmidt. I would like to welcome them up here. I will sit there, thank you. So please, and I will sit here on the side. So I would, sorry?
Am I allowed?
So I would like, before we start this discussion, maybe you could briefly introduce yourself to the audience, starting with you, please.
Okay, great. Hi, everyone. My name is Chimio Janvier. I am a solar and space physicist at the European Space Agency.
I'm Brian Schmidt. I am an astronomer at the Australian National University, having spent 8 years as the president of that university. That is a job I don't recommend unless you're really serious about wanting to run a university.
Okay. So I would like to invite you both, thank you for being here, to speak about your views about possible developments in your research field, breakthroughs and challenges in the first part of this session. So please go ahead.
Let you go first.
Okay, great. So as I said earlier, I'm a solar and space physicist, and you may wonder, what is this? So I didn't want to expand too much at the beginning. What it actually means is that I study the sun and the sun's activity and how it shapes the bubble of space we live in. So when I say we live in, I mean planet Earth and all the other planets of the solar system. And so one of the challenges is that the sun's activity actually peaks and wanes over time in what we call the solar cycle. And we have no idea why that works. So I would say that one of the major challenges is to understand this, but also to understand what the atmosphere of the sun is, how it is behaving. And the reason is because it's the place where we have all this activity, these eruptions, these storms that are going to be launched in space from the sun all the way to the ends of the solar system. So in terms of breakthrough, I would say that at the moment, I think we're on the verge of understanding this. We have a space mission that we launched 5 years ago, and it took us 5 years really to orbit around the sun and start to get out of the plane of the orbits of the planets of the solar system. And for the first time in the history of humanity, we are looking at the poles of the sun. And this is a missing piece of understanding how the magnetic field, this big magnet that the sun is behaving. So watch out this space for the next few years, I guess. Okay. Thank you.
All right, so I'm a cosmologist, and we live in a universe that is expanding. Everywhere we look, things are moving away from us, galaxies are moving away from us. The further away they are, the faster their redshift, or the larger their redshift is. Now, one of the things that a group of which I was part of that was eventually awarded the Nobel Prize discovered in 1998 is that the universe is speeding up over time. That was a surprise because gravity should be slowing the universe down, yet the universe appears to be speeding up. And we have resorted to something we call generically dark energy, but we normally think of as being Einstein's cosmological constant. It's a very single term that can be added to his equations of general relativity that actually would cause space to speed up in its expansion. It essentially causes gravity to push rather than pull. Now, trying to figure out what causes the actual expansion, is it a cosmological constant, is challenging for theorists because there are literally tens of thousands of ways to mimic a cosmological constant with almost no way to tell the difference between them. What astronomers have done, and I would say we've been sort of invaded by physicists as a discipline, is by doing bigger and bigger experiments where we're able to make more and more precise measurements of the expansion history of the universe back in time. And what those have started to show in the last couple years is a potential deviation from the theory of Einstein's cosmological constant. Now, the deviation is small, it's a couple percent, and I don't think we quite believe it. But it is there in the data, and we're going to get more data in the next few years to kind of see if it's statistically robust. We actually see it from two methods. One, the type 1a supernovae that we used all the way back in 1998, but probably more importantly, something called baryon acoustic oscillations, which are essentially the sound waves that the universe had in it right after the Big Bang that ultimately created structures and galaxies that we can see over time. So we have a problem in that the deviations are perhaps not expected, and the theory necessary to explain it, I would say after 20 years, well, even longer, 27 years now after the discovery, has still not really developed any smoking gun of what might cause a deviation like we're seeing. To make life even worse, we also have experiments where we compare the expansion rate of the universe right now as measured from our position, and then the expansion rate of the universe inferred from these baryon acoustic oscillations, which is essentially, you can measure them very precisely when the universe was 380,000 years old, and you can bring them to the present day using the model, and you can do that very precisely. The problem is they disagree by 8%. And the variation of dark energy is exciting. This, what we call the Hubble tension, is exciting, but no one has been able to figure out any way to do the same, the two things. They seem to go in different directions. So I would say we have a potential crisis in our understanding of cosmology, which 15 years ago looked like was really boring and we had sewed up and had everything down to the second decimal place. So I'm not quite sure how we're going to resolve this, but that's what's coming up right now.
Okay, thank you. So, me as a particle physicist, I immediately have one question to Brian. So we, in our standard opening lectures, when we motivate why we were looking for beyond the standard model physics, dark matter comes up, dark energy we mention, but stay a bit away from it. But what does this mean, this tension you just mentioned, quantitatively? I mean, I usually start my lectures or my presentation with that there's 27% dark matter in the universe, if you look at the energy matter content. But what does it mean, these tensions? If I would take these and vary it, how much would the 27% dark matter content vary?
So it turns out that the dark matter content, which is something I didn't talk about there, is another part of this piece where we need to have some undiscovered particle, potentially, that does not interact very often, or if at all, with baryons or with atomic matter that we have here on Earth. So the variation that we're seeing here is tiny.
Yeah.
So it doesn't really change that number much. What it changes is what happens in the future. So we tell a story. Well, the universe has started to accelerate. It'll accelerate forever. Eventually, we will look out into an empty universe. But if the dark energy is rapidly changing, then all bets are off of what the future is. Is it going to convert into something else? Is it going to just disappear, although you got to make this work in general relativity in complicated ways? I think it really throws into question what we could know about the future of our universe. And I'm pragmatic. At some point, I accept maybe I don't know. Okay. Maybe I'm never going to know what came before the Big Bang. Maybe I'm never going to know what the distant future of the universe is like. Maybe that's the answer. But I'd like to have something a little more definitive that I can tell in my talks.
So coming back to the sun, I have one. What I'm wondering is about. So you have said that's the first time we will look at the poles of the sun, and so could you, because I'm not from your field, explain to me why are you so excited about it? So what are the possible insights you may get, and then and the impact on, for example, life on Earth, or even neutrino physics, because the sun is also a source of neutrinos. I mean, could you develop a bit on that?
Yeah, okay, so a lot of questions in one question.
Yes.
I would say, so there are a lot of exciting things. I've only talked about the poles of the sun, but first of all, the reason why I said it's a missing piece of the puzzle is because, again, the sun and stars in general are big, giant magnets. And we have the technology now to measure the magnetic field on the surface of the sun, and then we can actually do that also for other stars. However, if you're trying to model something, if you can't see where most of the magnetic field is located at the poles, then you can't actually model it really, really well. And so that generates the question of, okay, so then how is the magnetic field of the sun structured? And we know that this magnetic field is what structures everything in the atmosphere of the sun, where we have those huge explosions that will eventually make what we call space weather, so the weather in space. So that's why it's really exciting to look at the poles, in the sense that it's uncharted territories. We don't really know what to find. And we like to, although what we have seen so far is not as extraordinary, I would say, as what we have seen on for Saturn and Jupiter. But we had missions that went to explore those two, what we call the giant planets of the solar system. And when Juno for Jupiter and Cassini, which were two missions that went and looked at the poles of these planets, they found structures that we would have never imagined. And this is what we're seeing a little bit about the sun. We are, from the first views that we had this year, we are seeing that the poles are actually moving and changing. And that might be one of the keys why the solar cycle is moving up and down over time. So now to your question about what does it, what's the consequences for us? I talked about space weather. So space weather is basically the changes in the space environment of the planets of the solar system. And for us, we are starting to put a lot of satellites. We are actually impacted, at least our societies are impacted by space weather. It impacts our telecommunication with satellites. It impacts also electricity grids. And so we are more and more reliant on this understanding of how the sun works. And so understanding how this magnetic field is generated, how it evolves over time, it's also a way of predicting space weather and mitigating the consequences of space weather on us. Now, something that I like to tell people is the reason why I went into astrophysics. I'd like to know why you went into the field. But for me, when I was little, I wanted to find aliens. So other life on other, well, to be fair, it's one of the other walls to be falling in the future, I believe. But what we're realizing is that us on Earth, we're really in the neighborhood of an active star, and we are discovering thousands now of exoplanets, and some of them are orbiting around very active other stars as well. And so that really raises the question of, can a planet sustain life, and in what form, if this planet, this exoplanet outside of the solar system, is orbiting around a star that is 1,000 times, 10,000 times more active than the sun? So the key question of what does the sun do and how it impacts us ultimately can be extrapolated to the search of life in other star systems. I haven't replied for the neutrinos, but I can talk a little bit about the particles aspect, because I think that's what you like. So not so much the neutrinos, because there are not that many changes, but what's really interesting is that the magnetic field of the sun, as I said, it really goes all the way to the ends of the solar system. It's actually a magnetic bubble that protects us from all the energetic particles that come from outer space. So we had a presentation earlier about blazars, for example. We have all these huge events, very energetic events in the universe. Some of them really send towards us what we call cosmic rays. And we actually are shielded by cosmic rays thanks to the sun. So it's not that bad.
Okay. Yeah. Thank you. So maybe you have some questions. I mean, this should be a conversation among you both. So or vice versa. Do you believe in
life on other planets?
Well, I mean, space weather is a kind of a mystery, because it connects into one of the themes of this, is into long-term climate change, or drivers of climate. So do you think you're going to be able to make predictions of the strength of the solar cycle on a 10-year, 15-year in advance, or do you think that's going to remain illusory?
I think we're getting there, but we're not there yet. And so the thing that has escaped us is we know roughly that this solar cycle is around 11 to 13 years, and we've known that actually since around Galileo's age, when we started pointing, well, not we, us, but back in the days when they started putting telescopes at the sun, and you can actually monitor this solar cycle with the presence of what we call sunspots, that are kind of freckles on the surface of the sun. And you can see that from the 17th century, that we have this oscillation in the cycle. But there have been in the past minima where there was no sunspots for years. And what we have seen so far is that we have a really some difficulties to predict what's going to happen even in the recent years. So we had predictions about the last solar cycle that were completely off, this solar cycle as well. And what we start to understand is that actually this 11 to 13 year cycle might be modulated by something that is even longer, maybe hundreds of years. And so that's why I mean by we're gathering more data. We have more of an understanding. We're getting there, but there might be something of a second order that is making us not, go in there just yet, if I may say.
Yeah, because the prediction, if you're trying to put up constellations of satellites, if you have a very big solar cycle, the atmosphere puffs up and it causes orbits to drag. And if you knew that were happening, you would put your satellites in different orbits and stuff, depending on what you could predict. Yeah.
Well, so I would say this is the long-term prediction in terms of the solar cycle. I would say that we are also going there in terms of more short-term prediction. And so we know where this space weather activity comes from. We have those sunspots. We can see them growing over time. And I would say that we are this moment in time where we see how complex they become. And we can't say with certainty whether one region of the sun is going to give a lot of space weather, but we have a good idea. And just as an example, there have been some Starlink that were lost upon their launch because there was a big solar storm arriving. So we knew that. Some people apparently didn't hear the scientists saying that that was not a good time to send satellites.
Coronal mass ejection, delay your launch, your launch, yes. Oh, well.
Yeah.
They'll learn next time.
Yeah.
So looking at the time, we have, maybe we can open up to the audience for questions to our discussion partners here.
Yeah, hi. Do I have to switch it on? No, it's okay. Yeah, hi, thanks. I would have a question actually regarding cosmology. So, Brian, to you. I was aware about the interesting question of is it dark energy or just a constant, cosmological constant, and I believe Euclid is looking after that. That was recently launched. However, I was not aware that there's already some signal that maybe it's really changing over the scale. So this is really new to me and exciting to hear. May I ask, where is it seen? Is it at small c or large c values, or is it in and how much sigmas, if I may ask?
Yeah, okay. So the signal has come out in the last 12 months. So it's seen in 2 experiments. One is called DESI, the Dark Energy Spectroscopic Instrument, which has literally looked at tens of millions of galaxies. And then they're looking for essentially the sound scale that is imprinted in the cosmic microwave background. If you see this early all-sky image of the leftover of the Big Bang, when the universe was hot, there's actually an acoustic scale there that has a size that is imprinted in the galaxies. And when you go through and look at that sound scale, it changes and deviates at about, depending on how you look at it, between a skeptic would say 2, the team would say 4 standard deviations. That is about a 2% effect, and the redshift is at about 0.3. So what it's basically saying is that the universe was accelerating, and then as soon as the density of dark energy became dominant, it started fading away, and essentially its energy density no longer was constant, but seems to be dropping now. That's what the data to first order says. So you're going to have Euclid. You're going to have the second half of the DESI data. You also have supernova experiments, which, if you look at that, see potentially a signal that is consistent with the DESI signal. Now, the supernova are right on the hairy edge of what you can do right now. They've kind of done what they can, in my opinion. So I think these baryon acoustic oscillation measurements over the next couple years will, first thing I want to see is with a completely independent set of data, do you still see the signal? And then we need to make sure there isn't some weird systematic error that can creep in. It's a pretty hard to mess up signal. So I'm more optimistic on that. But it's kind of exciting. It's a mess. All my beautiful talks I've been giving for the last 20 years are kind of, and yeah, I really don't know what's going on. So that's a little disappointing. But that's science. It means my field still has a rich future.
Yeah, thank you. So I saw first this, and then there.
So my question was to Professor Schmidt. What's your perspective on the next generation of space missions that might help you resolve the tensions that you talked about? Because there's heliophysics at one end where the source is in our backyard, and then there's like black hole imaging missions which go like to the distant black holes. And there are complications with CMBS-4, as we all know. So is there a science case to be made for next generation space missions?
So there's a whole bunch of things we can do. And one of my challenges, and I'm not going to sound like a cosmologist here, is the cosmology missions are huge and tend to be kind of single purpose. So you literally go through and you take 100 million lowest signal per object measurements you can, and at the end of it you crank around and 100 people spend 10 years of their lives and you get an answer. That's not a very rich experimental environment. Then you have something like James Webb Space Telescope that, you know, everyone and their dog can use the data to do all sorts of things. So I think we need to have a balanced portfolio where we keep on doing things where small groups can be very creative and we make new discoveries, and then we have to be very selective of the type of giant cosmology experiments we do. And you know, there are rooms to do things like solar missions, which I think are really important and interesting, that are completely different. So I think we need to be portfolio based, and I would be very careful at squeezing out instruments in the future that have thousands of different projects that can be done as opposed to just single purpose experiments.
Okay. Please. Yeah. Okay.
Thank you. I have tried to keep myself away from physics my entire life. That's why I studied geology. And when they explained me in the first place the changes of climate in the Earth system, they spoke about the Milankovitch cycles. And that's a theory that is already 100 years old. Speaking about solar system weather, what could you tell me that, is there any other cycle or phenomena in the solar system that conditions the climate of the Earth in geological timescales?
It's an interesting question. I would say that it's a tricky discussion to be had with people who are really interested in the climate, in the sense that